everyone, and welcome to Learning at 11th Hour. So, this video is going to be about the importance of don't care conditions in Kmaps and what are the real time applications of these don't care conditions. What do they really mean? Right? So, to explain that, I'm going to take up the example of BCD to XS3 code converter design. So, what is BCD? BCD basically stands for binary coded decimal. So we know that the decimal has only 10 symbols starting from 0 to 9. That's the decimal number system. Now we are going to code these decimal numbers using binary. So if we have to do that in order to code 10 numbers, right, we will require, or in order to code 10 symbols, we will require how many digits or how many bits in the binary. So if we take 3 bits, 2 power 3 would actually be 8, but we need 10 symbols. So therefore, we require 4 bits so that we will have an option of being able to code 16 symbols, of which we are only going to use 10. So now, if you look at this small table shown over here, I have shown you how we are going to be able to represent the symbols 0 to 9, the decimal symbols, using binary. So the first row represents 0, the second is 1, 2, 3, 4, 5, 6, 7, 8, followed by 9. So if I have a number like 243, which is in decimal, and I want to convert it into BCD, then what I need to do is I need to express each of these digits in this binary coded system. So 2 is going to be 0010. 4 is going to be 0100 and 3 is going to be 0011. So all put together, this is the BCD representation of 243. So having said that, I am now going to show you how we can convert this BCD system into an XS3 code. XS3 meaning, as the name suggests, it's going to be 3 XS from the actual number. So say I have 0 over here, the XS3 would be 0 plus 3. So this should have a 3. If I have a 1 here, this should be 4, and so on. So if this is 9, this is going to be a 12. So this is the XS3 representation, right? So whatever number we have, XS3 of that will be represented in this number system, right? So we are now going to see how we can convert BCD numbers into XS3. And while doing that, I'll tell you where we are going to have the don't care conditions coming up. So this is the truth table that I'm going to fill up right now. The B's, right? These are the 4 bits for the BCD, and the X's. These are the 4 bits representing the XS3. So this is the XS3 representation of these BCD codes. So if I have a 0, I should start with a 1 here. So 0011. And then I can add 3 continuously to each of these BCD numbers and fill up this. So 0100, 0101, 0110, 0111, 1000, 1001, 1010, 1011. Now, if you notice, this is nothing but 8 of my BCD. And the last number that is there, it's going to be 9. So I'll have 1100. So with this 9, my BCD's number system has actually got over. So this is the set of BCD numbers that I've actually got. But when I design a circuit, a black box, say, when I design a circuit which acts as a BCD to XS3 code converter, I'll be having 4 inputs, right? So B3, B2, B1, and B0. And I'll be getting 4-bit outputs. So X3, X2, X1, and X0. Now, when I test this black box, I cannot restrict the user saying that you should only test it for numbers 0 to 9, it should actually work completely, isn't it? So to say, if I have four inputs, the combination of all the four inputs, that is 16 possible combinations, would be applicable or applied to this particular design. In that case, if you notice, these six inputs that we have, starting from 1010 to 1111, they are actually inputs which we do not care about because they do not fall under the BCD code itself. So there we have, we do not care about these inputs. So therefore, these are don't care inputs, and therefore the outputs of these would be represented with don't care symbols, which is nothing but a simple cross. So we fill up these as X's or cross in this manner. After this, we need to design a circuit such that we have got expressions for x3, x2, x1, and x0, which we can simplify using the Kmap and obtain a simple optimized circuit. So the first step now after this is going to be to find the expression for x3. So this is going to have the terms B3, B2, B1, and B0. So it's a 4 cross 4 K map which we need to draw. Here we have B3, B2, B1, B0. This is going to be the gray code representation. Now we can fill up the squares corresponding to x3, right? So here we have for 5, 6, 7, 8, and 9, we have 1. So let's write out the numbers 0, 1, 2, 3, 4, 5, 6, 7, then go down 8, 9, 10, 11, 12, 13, 14, and 15. So for 5, 6, if we notice, for 5, 6, 7, 8, and 9, we have ones. So we'll mark the minterms 5, 6, 7, 8, and 9. Apart from this, we have don't cares, which will also go into the K map. So this is for 10, 11, 12, 13, 14, 15. So we'll put don't cares over here. Right. Now, how do we group it? Right? Do we at all use these don't cares? Yes. So here we see that the don't cares could be used or considered to act as ones in this case. Don't care simply here means this could either be a 0 or a 1. We don't care whether this particular input is occurring or not. If it does occur, this output could either be a 0 or a 1. So that's what the don't care condition means. So we are going to be using these don't care conditions and considering them to be acting as ones when we are grouping min terms. If you are going to group for max terms, then we can consider them to be zeros also, right? So now framing the groups, right? So the larger the group, the better it is. In that case, if we see, we have this particular group available. So here, if you notice, these two ones are grouped along with these don't cares, considering that these don't cares are acting as ones right now. So the expression for this particular group is going to be B3 because it's spanning across these two rows and only B3 is consistent in both the rows. If you look at the columns, since it's spanning across all the four columns, it's going to obviously change. B1 and B0 terms are going to change from 0 to 1. So they will not be involved in the expression. The next group that we can form here is to group these two ones. So for that, we can use these two don't care conditions and form a group, a quad in this manner. So when we look at this quad, we see that this is going to be B2 and B0. So that is the expression for this quad, right? Now there's one more one which is left. Now the larger the group, the better it is. So we can group it with this, another quad. where the expression would be B2 ANDed with B1. So the expression for x3 therefore becomes B3 plus B2 ANDed with B1 plus B0. So this is the expression for x3. So if you notice, what has our don't care condition done? It has actually helped us to form or frame larger groups, thereby helping us to simplify or reduce the size of the expression, which in turn will reduce the size of the circuit which we are going to implement. The most important thing that we need to understand is you cannot have a group with only don't care conditions. So cannot group don't cares alone. It should be grouped along with some other minterm or max term. It cannot be grouped only as a separate group. For example, if you look at this row, this has four don't cares, and therefore you might think that this could form a group, but they are all don't cares, so they are not going to be valid term. It will just add to some redundancy. It's not going to be a valid term in the sense that that particular input itself is not valid. For example, in this case, right, so the BCD is only valid from 0 to 9, so rest of the inputs correspond to the don't care outputs. So therefore there is no point in grouping just the don't cares. Having said that, you can go ahead and find out the expression for x2, x1 and x0 in this similar manner. So here I've marked the minterms for x2, and I'll just show you how you can frame the groups over here. And so this is going to be one quad, right? The larger the group, the better. Again, this could be another quad. This is to group this particular minterm, right? And we have to have a pair over here because it's not, there is no don't care over here. Otherwise, we would have framed a quad also. So these are the three groups that are there for x2. I'll give you a small exercise and I'll ask you to kindly find out the expression for this x2, right? I'll show you how you can group it for x1 also. So here the minterms are 0, 3, 4, 7 and 8. So I'll mark it as 0, 3, 4, 7 and 8, and the rest are don't cares like this. From 10 onwards, it's don't cares. So here we can see that there are actually two quads formed vertically. Okay, so we can frame groups like that. So this is one quad, this is the next quad which we have, and that's it. All the minterms have got included, right? So the expression for this, that is for x1, is going to be b1 dash b0 dash plus b1 b0, which we know is nothing but x nor. So b1 x nor of b0. This is the expression for x1. Okay, and in the same way we can actually fill up the minterms for x naught. Here we see it starts from 0 again. 0, 2, 4, 6, 8, right? All the even numbers. So we have 0, 2, 4, 6, 8. And from 10 onwards, the rest are all don't cares. So how do we group this? So here we see this can be grouped as an octet because we can fold this Kmap along this vertical imaginary line, and the two ends would meet and lie adjacent to each other, and therefore this would form an octet. And the expression for octet and therefore this x naught would become It is spanning across all four rows, so therefore B3, B2 would change. It is spanning across these two columns, and here only B naught is the same. It is 0 in both the cases. So we'll keep it as B naught dash. So the expression for this octet, and therefore the expression for X naught, is B naught dash. So this is how we can find out the expression for all the um 4 bits of the XS3 code, and then we can implement it using logical gates, right? So so that when we have inputs given in the BCD form, we'll actually get outputs in the XS3 form. So this is just a simple implementation of the expressions that we've got right now. Here we have B3, B2, B1 and B0, which is the BCD input, and X0, X1, X2, X3 are the XS3 outputs. So we know that B0 dash was X0, so I've just included the NOT gate to obtain B0 dash right over here. This is actually the XNOR gate. So B1 XNOR of B0 is X1. I had given you an exercise as to compute what X2 is. I'd like you to find it out and fill it up here. It would be looking similar to X3 with more number of expressions in it, right? More number of terms in it. So it will have a set of logic gates. So here X3 was actually B3 plus B2 dot B1 plus B0. So that's exactly what has been implemented over here. So in this manner, you can use the don't cares to form smaller groups. And I hope you've understood what are the scenarios where don't care conditions would occur. So it's basically where the inputs are going to be invalid. In that case, we can consider the outputs to be don't cares. And we can use them in Kmaps to frame the expressions. So that's all with today's video. I hope you've understood the concept of don't cares as well as BCD to XS3 code conversion. Please do subscribe to this channel, and please drop in your comments if you have any queries. Thank you.